Alright, let us have a look at example 8.6. In this example, you will find that you are going to make use energy potential of a spring, whereby you are going to calculate that work, and at the same time, okay, it will be separated into two. Questions will be asking you if that the system is frictionless, so no friction, while B, there will be a friction. So two types of question. Alright, in this question, you have a block of mass where it's on a horizontal surface, hence a horizontal spring, having a K value, spring constant, 1000 Newton per meter. In this case, you were given initial situation, a value of negative 0.02 meter because of compression. Okay, so make sure convert into SI unit because we are dealing with unit joule, which is work. And when it is at this position, it is actually at rest. While it is being compressed as in this figure, so this is the initial position, it is compressed. Okay, it is compressed and then released. So at this position, it has initial speed as 0. The question is asking you to calculate speed when it passes equilibrium. So this is our final position, provided that the system is frictionless. So in the case of it's a frictionless, you will find that we can use two methods. As portrayed by the book, we're using work energy theorem, where work is now supply, the change of the kind work is supply ataupun work is done by the spring on the system by using half kx squared, or perhaps from high school, half force times x, and indicates that the force is spring. This is high school. Alright, so look at how it's substituted. So this expression would be here. So we find that change of the kinetic energy is equivalent to half kx squared. Now substituting the initial as 0, so the initial as 0, you will find that, so this is 0, 0, okay, and x maximum as a product of 0.02 meter, so make sure that you substitute correctly. Then you are left with an unknown, which is V final. Okay, V final. How about mass and the rest? It's here, K and such. Okay, you just substitute accordingly. Masukkan ikut apa benda dia. And you will find that your answer plus minus is 0.5. Okay. Now in the case here, since it's asking for speed, then it's enough to jot down as 0.5. Now how about if you choose the technique where energy final minus energy initial equivalent to 0, which in this case actually equivalent to delta kinetic energy plus delta U, equivalent to 0. Now this is 0 because work non-conservative is 0. Tak ada friction, maka it's equivalent to 0. So observe how I do the substitution. Now the V final occurred here. The V final occurred here. So it remains an unknown value. So just now, we did mention, according to the question, that the initial is 0. Initial 0 because that occurs here, position here. And at this location as well, the compression is this much. Alright. While when it passed through the equilibrium, which is the final position, there is no compression. So look at how we portray the x value. And from here, you should just rearrange and you will get back to the given answer, which would be 0.5 meter per second. Alright, let's now look at situation. What if the system has friction? And therefore, the question is, calculate again the speed. Same position, which is final position at equilibrium, sorry. provided that now we have one value of friction which is a constant value. And therefore, this is the work non-conservative. Retard ni maksudnya menghalang ataupun slow down, alright? From the moment it release, okay, slow it down. So kita akan expect that our final answer 0.39 is actually less than the original if without friction, 0.5. But then again, how do we do the process? Now, the one which portrayed by the book is equivalent to the one that we shown earlier. It's just that rather than have the work non-conservative as part of the system, kita letakkan sebelah kanan ni sebab to indicates that the external. Tak ada masalah pun. Alright. So this one is here. So they are of the same thing. Alright. The next thing is, observe that this is a positive value while this is a negative value, which is cos 180 ni memang kita akan dapat as equivalent to negative 1. And then substitution, okay, substitution look quite similar. Sama sahaja dengan apa yang you substitute earlier. For instance, you akan nampak U sebagai kosong because that occurs at equilibrium. Okay, at equilibrium, and this is the one yang kita nak tahu. Okay, and then nampak ni U dia 0. And then X displacement final. So this is final displacement, which would be final, not friction, final X. So which is 0 at equilibrium. And the initial is compression, negative X squared lah. Alright. Now arranging both, either this technique or this technique, they will arrive with this answer. Sama sahaja except now kita tambahkan work non-conservative ataupun by the book punya version, we include delta internal energy, which is actually loss. So this is where it's I would say that non-isolated system. It's just that your book is actually putting in together. Maknanya dia macam jadikan dia sebagai isolated lah. Cuma kalau this technique, memang this technique adalah non-isolated. Because friction now ada tendency to take away the energy. Alright, so this version is actually equivalent as well if we jot down dalam bentuk energy final minus energy initial, then this work non-conservative is actually energy loss. So that's the reason why the answer is negative. Sebab apa? Kalau kita put some number, mungkin energy constantly adalah 500. Tolak 500, dapat 0. Tapi kalau dia loss, then perhaps loss 50, then kita nampak 450 minus 500. Ada less 50 kan? Ada kurang negative 50. So that's the idea of concept energy loss or work non-conservative. Alright, 8.4, changes in mechanical energy for non-conservative force. Alright, we discussed this earlier in the previous example. So I did mention that the change in the internal energy due to the friction is actually non-conservative force. And for that reason, I am arranging it here. Okay, so due to the friction. So I am considering that it's coming from the external. But in the book itself, okay, the change here is actually part of the system. Dia masukkan part of the system. Right? And that's the reason why they put it as here, adding it up. Right? Alright, we are going to look at example 8.7. Now, in this 8.7, you will find there is friction throughout the motion. The whole distance of motion tu, travelling distance by the object, akan ada friction. Cuma isunya is much easier because kita akan nampak ada satu value saja. Kita don't need to calculate the force itself. Okay, what I meant here, this is a crate. Now, this crate is 3 kg. Originally at a position on top of a ram, which is kita labelkan sebagai A. Now, this whole distance of the ram is 1 meter. Throughout from here until B, okay, adalah 1 meter. And at an angle 30 degree as shown. Now, the crate start from rest. Alright, terms rest, remember initial speed is 0. So let's put some number here. Right? And then it experienced a constant value of force with this magnitude 5 Newton. Throughout, from A until B, there is friction equivalent to 5 until it continue to move another short distance on the horizontal floor from here to here, B to C. So meaning that the whole distance that it has travelled from A until the ground, and then on the flat ground continuing towards the end one point position farther, which is C, for instance. So what happened then? It comes to rest. So we have a V final equivalent to 0. Now, the question, by using energy methods, okay, it doesn't say that a work energy theorem or conservation of energy. So, it's up to us then. Find the final speed at the bottom. Now, what we are going to do is we are going to choose two position to be initial and final. And in both case, ada dua teknik kat sini. We are going to say that A is the initial while B is the final. Alright. Now, observe something before we proceed. Recall again that calculating work is by using force time displacement and the angle between them. And therefore, you will find that as the object continue moving downward the ramp, this is how the displacement, or perhaps we tend to write as delta R, and the direction in the opposite motion would be the direction of the kinetic frictions. And that's the reason you find that their angle 180 and effect to that is negative friction. Alright, observe something here. We have the same expression. It's just that the arrangement is a little bit different. Ada beza pun. So you can choose any of the two method. But I will go with this technique throughout our discussion. Sebab kita nak maintain one singular technique. Whether there is friction or whether there is no friction. Right now, into it, you will find here that as you consider B as the final, B as our final, hence you will find that velocity at that location here is an unknown value here, the same as this one. This is actually our V at B location. And how about at initial? This is at A, which here equivalent to 0. So that's how you kind of substitute, yeah. And how about your final? Okay, final. This is the location. So the Y at B is at 0. So that's the reason why you have 0 here. And the initial here represent a positive value of 0.5. Alright. Now, how about, okay, since I'm looking as well as this one. So this is the 5 value. Okay. The rest of delta is similar to us as you compare book and also my writing. And how about D? Now, observe here that the D or the delta R here is between A and B. And that's the reason why it's equivalent to 1 meter. 1 meter. Alright. Now, this is the one we are talking about. 1 meter. This is delta R, which is this one is D as well. Alright. So, complete the calculation. You will arrive with this number 2.54 meter per second. And again, this is square root. So, that's the reason why it's asking for speed. Because you might have a tendency to put whether it's positive or negative. So, just ignore the positive or negative. It's just this, a number. Now, the next question B, how far it slides on the horizontal floor. If it does experience the same magnitudes of friction, 5 Newton, which is a constant value. So the question is asking for distance travel between B and C. Distance travel between B and C. Alright. Now, there are two methods here. Okay. Shown here, as you are aware from the very beginning, it's just the same. It's just that we just arrange the concept of friction, work by the friction on the other side of the equation. Bezanya itu sahaja. Alright. Notice here, if we did take consideration that our position of interest is between A and C, now the substitution of kinetic energy between both position is zero. Why? Because eventually it stopped. By the time it reached here, C, it stopped. So that's the reason why it jot down as zero. How about the beginning? A, the A indicates that U is zero. Alright, so that's the reason why kinetic energy 0 minus 0. Alright, how about the potential? So again, you just look at the similar technique earlier. Okay, sama sahaja. That 0.5, this is 0.5, 0.5. And the final is at the ground, which is at C. So no elevation, tak ada ketinggian pun. Masih lagi dekat ground yang sama. So that's the reason why dia kosong. Right, let's rub this. Now, the thing is, something throughout your calculation, you will arrive with 2.94. So 2.94 is actually a distance travel from A, B and ended at C. Since it's asking for the additional distance on the horizontal, so that's why you subtract 1 meter. So with the answer of 1.94. Now, how about you choose the position between B and C? Now, therefore, you will find that at B location, the speed is 2.54. Okay, the initial speed is 2.54. So it's correspond to that. And hence you will find that the displacement or distance travel is just between B and C. A straightforward answer of 1.94. Tak perlu tolak-tolak lagi sebab indicated here you dah pilih antara B dengan C sahaja. Understand? Now, example 8.8, right? In this example, you will find that we are going to consider two situations. Again, friction and without friction. Number one. Number two, there will be an additional types of energy coming from spring. Okay, coming from spring. And both case, we do not have elevation. Okay, no elevation. So energy involved would be kinetic and also potential. So what is the case? The scenario is if the mass of the blocks is 0.8 kilogram, it is pushed to the right with speed 1.2 meter per second or velocity, so therefore positive velocity. It then collide with a spring which mass is negligible, so don't bother, and a constant of spring which is 50 Newton per meter. Now, as shown in the figure below, in the case of A, picture A, you find that the block has kinetic energy. Okay, and the moment it hit, so you find that that's the reason why the energy at this position is jot down as half mass of the block and its speed square root. Its speed square. Now, you find when it's partially or halfway of compression, the energy is a mixture of kinetic plus potential energy of a spring. So this is kinetic plus potential of the spring. So but the amount should be equivalent. And then when it compresses fully the system, the kinetic energy turns to be zero. Why? Because once you compress to the maximum, object is about to U-turn. Nak balik ke belakang. So, the kinetic energy, the speed will be 0 at that location. And therefore, the energy at that moment is fully in the form of potential energy. Spring potential energy. So that's the reason half K, and we say that this is maximum compression or displacement. Okay. And then, the moment it return backwards, okay, provided there's no friction, energy is conserved. So, you expect that the whole energy would later on be converted back to kinetic energy. So, KE okay. So, that's the reason why half mv squared to indicates that if this is 1.2, this is 1.2 squared, then this is 1.2 squared. So it get back what it has given earlier. Maknanya mula-mula punya full kinetic energy, then dia give off to potential supaya spring compress, and then when it goes away in the opposite direction, no longer interacting with the spring, then dia gain back dia punya energy waktu awal-awal, the kinetic energy. Now this information would then be used to calculate maximum compression provided that it's frictionless. So we tend to write down our technique previously. Conservation of energy, delta kinetic energy plus delta spring potential, then equivalent to work non-conservative. However, in this case frictionless, so work non-conservative is 0. Alright. So we need to choose position. So our position is A and C. Let's double check what is A. So A when the energy is half mv squared. C is when energy is in the form of half kx squared. Okay. Now if you are using this technique, okay, this is how you substitute. So when it is at C, so notice that this is final, which is this is final. This is initial. So notice that V at C is 0, indicating here as kinetic energy 0. And at A just now is 1.2 meter per second. And then final compression. So this is final compression as compared to previously when we at A, what happened? Sorry, what A? Let's have a look. At A, there's no compression at all. So that's the reason why this is 0. Okay, referring to A. Okay, and solving, you will arrive with answer 0.15, and this is actually at C, and as well maximum compression. Alright, in B question, you will find that you will still consider position A and C, okay, where C is our final, A in our initial. However, there will be a friction. And in this case, you are required to calculate it. How? By combining the idea that you have learned in the previous topic, that friction is coefficient times the normal force. And again, since it's a flat surface, the normal force is equivalent to the weight itself. Alright, now, so what to do? The same technique as the previous. Sama sahaja. Cuma we are adding the work non-conservative as something to be discovered. Perlu dicari. Okay, perlu dicari. Bukan lagi kosong. Tak sama dengan kosong. Work non-conservative is not equivalent to 0. It has a value. Now, same as this one. Sama Alright. Now, you will find that, let's focus first on the work non-conservative. The expression earlier, the force times the normal. Okay. The force times the displacement and times 180, cos 180. The product of cos 180 is -1 again. And observe that the friction can be calculated by using this version. Coefficient times mass times gravity. Okay. And again, something to recall, don't ever consider to have negative. It's just purely positive 9.81 because you have considered all direction in this example. However, something to understand a little bit extra, bear in mind the x that you are going to calculate, which is distance at C here, will be a new value. A new value because now energy is getting lesser. Dah hilang sikit kepada friction. There will be energy loss. So, if you remember, delta K plus delta U is also correct to jot down as total energy at C minus total energy at A. And now they are not equivalent. Diorang tak sama nilai. Dah jadi kurang dekat A sebab friction ambil sedikit. So that's why we jot down as energy loss. Right? And substitution is similar to the previous. Sama sahaja as A. Sub as A, sama sahaja substitution dia. Follow the same technique except for this one. Ini sahaja hashtag ataupun star, teknik baru. And you will find that you arrive with an X new which is less than 0.15 to indicate that at 0, if it's 0.15, there is no friction. Jadi dia bolehlah jalan jauh sikit. Sebab energi tu tak ada diambil oleh friction. However, yang ini sedikit energy is taken away to overcome friction. So you find the distance travel now slightly less before come to rest. Okay. Now in example 8.9, you are about to see there are two blocks move together simultaneously. So you will find that they would have similar value of displacement. Okay. For instance, you find that in the picture, if M2 falls down through H distance, and M1 should be displaced, bergerak sebanyak the same amount of height. Only that one is in the vertical and the other is in horizontal. Now, you will find that we have three objects in this question. Number one, mass. Number one. Number two is mass hanging mass. And number three, the spring itself. And these three, we can consider as a system. Therefore, the expression of conservation of energy will now be including change in the potential energy belonging to the spring. Now, altogether, we have three types of energy that we are going to combine into 1, 2, 3 simultaneously. And you will find that as well, we are going to see there is friction, and because of that, there is work non-conservative. Alright, let's have a look at the question. Two blocks, M1 and M2, connected by a light spring, passes a frictionless pulley. Now, it's the pulley which is frictionless. It's not the surface. Alright. So, the block M1, as in the picture, is on the flat and horizontal surface and connected to a spring. Okay, the fact that it's connected to a spring, therefore we will find that there was this internal change, or potential energy belonging to the spring. With force constant, not value given, so only K is symbol. Now the whole system, okay, it does put some keywords here. Release from rest. So initial speed of the three things. Sorry, not included 3. Okay. Mass 1 and mass 2 will be 0 when it is unstretched. So the initial condition is x is also 0. If then M2 fall a distant downward h before coming to rest, so the term to rest, come to rest indicates that their V final would be 0. calculate the coefficient of kinetic friction. So this is the main question. They would like you to calculate the mu between the block M1 horizontal and the surface. Now, so observe that the keyword rest just now appear twice in the statement. This is to indicate the initial and the final. The initial and the final that both have this one, and also this to indicate that they are 0. And as you do the calculation, okay, remember the equation earlier that I have shown you. It's just that rather than have it here, okay, we are arranging it a little bit differently. But then again, you are free to choose whichever suitable that fit into your understanding. And again, recall here that it should be cos 180 when you calculate the amount of work non-conservative. And now, important things to understand. Remember earlier when it does says that M2 will fall through a vertical distance of H, and hence the distance travelled by M1 would be as well the same distance, but only occurring flat surface. Maknanya yang satu tu jatuh, contoh M2 dia jatuh 5 cm downwards. So it's only logical because diorang connected, maka M1 pun akan displaced by 5 cm. So sama jumlah tetapi pada arah horizontal. So that is the reason why you will find here in the expression of internal energy, potential, the friction, the D value is being replaced with H. Alright, so same as mine. Now, the thing about the kinetic energy earlier, remember that it does say something appear twice. Okay, appear twice. So, indicating situation internal and kinetic energy now is 0 for both object. For both object, we are looking at both object, yeah. For the motion. And now how about potential energy? It turns out only M2 sahaja. Only M2 sahaja. So only M2. So this one is actually belonging to M1 and M2. Alright. And M2 we find that has traveled. Go back to the question. We find that the M2 finally has gone downward. So downward. So we find that the M2 potential energy is this much. Okay. But here we will find that we can choose, okay, reference level kita. If you choose it here, okay, then the final would be 0. So the final would be 0 because here the final position is noted as 0. And therefore, elevated up initial position. Ni initial This is now initial position. This is initial position, this is final position. So you find that's the reason why we jot down as 0. Okay. Now how about the spring itself? So finally, this is the final situation. Remember again that it's supposed to play around with this expression. Okay. So here you also see that the X and H are being replaced using the same symbol. Supaya kita tak confuse, as if X benda lain, H benda lain. So you just have to use the same symbol. And there is no stretch, okay, at the beginning. So this is how you construct the equation. Right, as you simplify the expression, once you have understand and simplified, therefore you arrive with this. Okay. Now my concern is that you are able to understand how you come and arrive with this expression. Okay. Right. Now let us have a look at this example. Now in this example there is no frictions. there is no friction at all, so it's supposed to be easy. And we find that we have two objects that we will say as a system, 4 kilogram and 3 kilogram. Alright, how is the arrangement? We find that the heavier, which is 4 kilogram, originally placed and up here a certain elevation h, and then release from rest. Okay, so release from rest indicating that it has kinetic energy is equivalent to 0 and V or U is equivalent to 0. And therefore, if the question is asking you using isolated model, isolated represent that only these two objects, no friction, determine speed of mass number 3 just before the 4 kilogram falls down and hit the tables, just right before. Understand? Right, now what happened in the process is when 4 kilogram falls to the table before the impact, you will find that they have the same final value. They have the same final value, right? So the question asking speed of mass 2 can as well be correct if it's asking for speed of mass 1, okay, just before it hits the table, because they have the same value. Now, why did they have the same value? It makes sense because both are connected by this string, so they move simultaneously together. Okay, now how do we process the info then? Okay, by using that the idea they have the same V, right? Um, we will see here, okay, the expression to be used. We will consider there is no friction, so delta kinetic energy plus delta change in gravity equivalent to 0 because there is no friction. Right. Now, look how special we treat the idea of kinetic energy. In this case, you will find that originally, the kinetic energy initial is 0 for both, for mass 1 and for mass 2. So this is actually minus 0. So this here, portray here, represent the situation for the final, where this one belong to mass 1 and mass 2. Mass 1 and mass 2, right? So two objects simultaneously we look at their kinetic energy. Now, how about their potential? Observe as well, we actually consider for again mass 1 and mass 2. And for the same reason, we find that M1 here loses, okay, negative, loses potential energy, and M2 gain potential energy through the same H. Now, you can do separately for delta U for mass number 1 and then add it with delta U potential gravity for M2. You will end up with this expression, the same thing. And once done, sum up both like what they did just now. Okay, you have the expression, simply add or substitute the value of the mass and the initial height, okay, and you will arrive with the required answer. So again, this 2.59 is the V final for the 3 kilogram and as well the V final for 4 kilogram. Now let us look at B. Now this question will be asking you what will be maximum height from the table, right from the table, where 3 kilogram object will rise up. Now, what happened in this scenario is by the time 4 hits the table and stop moving, so you find that the string slacken, okay, tension disappeared, and at this y 2.4 meter, okay, at a distance of, which is h just now, this is h, okay, it had gained speed, which is 2.59 meter per second, the answer that you have calculated earlier. Okay, with this amount of speed, it then continues moving upward, similar to the concept of free fall. Okay, free fall. Again, ask yourself, why is it there is no effect of tension? Because 4 kilogram already hit the table surface, and therefore tension in this case is actually turns to be 0. So we find that the only acceleration 3 kilogram will experience is only the acceleration by the gravity, which is negative 9.8 meter per second squared. Now, we have two options here to solve. Number one, we can choose to write down in using kinematic. You can use using kinematic, considering when you reach the highest position, the V will be 0 and the initial is S 2.59. So substitute into kinematic, you will get the answer. However, the answer that you are going to get here is just 0.34 meter. Now 0.34 here is not yet the answer, because this is just the additional distance travel. Is the additional distance travel. So you have to add up with 2.4 meter, which is the height to original height earlier, right? However, okay, now let's turn to using related expression we learned in chapter 8, which is conservation of energy. So look closely here. This is the equation that we are going to use. And our non-conservative force is 0, no friction. So 0. And our system is not M1, sorry. Our system is purely M2 now. We are no longer concerned about the heavier object. Now it's just the mass number 2. So look at the kinetic energy. You find that by the time the object reach, okay, let's look at the picture. So when it had reached the maximum height, you will find that, okay, its V would be 0. Okay, by the time it reached the highest position, the V would be 0. So since that is the case, that is the reason why the change of the kinetic energy final minus initial is jotted down as this way, right? Now, how about the substitution of the V values? Hold on to that. Okay, how about change in the potential energy? So you find that we are going to leave it as a delta H to indicate we would like to know what will be the additional distance travel, the overall travel distance, okay? And with that, okay, as we do our substitution, so this is the initial speed, similar to this one, 2.59, okay, and leave H final minus H initial as delta, and look closely at how we substitute the value of G, a positive value, And once you have done with your calculation, observe that you arrive with the same answer similar as using kinematic, which is positive 0.34, to indicate that this is the additional distance travelled but in the direction upwards. So therefore, the total distance or the total height from the table becomes 2.74 by adding with the original height as in figure. So where is 0.34 in our figure? 0.34 is here, 4 meter. Alright, this is our last subtopic, which is power. But before we jump into power, let's wrap up the idea of conservation earlier. You will find that in the whole idea of the book itself, notice here, it's actually trying to say that the system is composed of the internal energy, which actually comes from friction. But what I shown you, the other part is the internal energy is outside. It loses, okay? So in this case, you find as well that the energy can be written in the form of energy final minus energy initial, okay, equivalent to the work non-conservative, energy loss, right? Energy loss. So that's the reason why you find that work by the friction is negative. Okay, on the other hand, it's also correct to write down as change of the kinetic energy. It's the same as this one. It's just that the way you write it down. So it becomes an equation where you notice that there is kinetic energy, potential energy. We remember that it can be separated into two. Number one, spring. Number two, gravity. So it depends on the question itself, and this is work by the friction. And equivalent to, most of the time in this textbook, you will notice that we are not so much into using heat and other things here. We are more on the work here, equivalent to the work. So work energy theorem can later on be associated to, if you remember, work energy theorem then would be simplifying this expression where delta K is equivalent to work itself. Alright. Now, the way that it's describing isolated and non-isolated is, for our case is, you find that non-isolated, I did take out the internal energy belonging to the friction. And in the case of the book itself, it try to say that when it is isolated, you find that the friction is now considered part of the system. So if let's say, if there is no friction, change of kinetic energy is equivalent to 500. This is negative 500 then. But when there is friction, you find that this number reduced to most probable 300. And that makes then that the internal energy or frictions another number, which is the negative 200. So 3 plus 2, 300 and 200 when adding up make it becoming again the original without friction. Okay, this is just an understanding. Alright, let's now turn to power. Alright, let's start with how do you calculate power, right? Now, in this topic of concept of power, you will find there are two versions. Number one, we call it average power, and another is instantaneous power. Now, the terms instantaneous, at specific instant, at that instant. So, a specific time, right? What will be the power. So overall, these two has the same unit. It's just that to portray the situation. So unit is joule over second, or we call it watts. Okay, watts. Now, in another way to convey what is power, okay, in ordinary version, it's how much energy used in within 1 second or expanded digunakan dalam tempoh 1 saat. For instance, 5 watts present 5 joule in 1 second. It means that in 10 seconds, 50 joule of energy, 50 joule of work is expended. Okay, 50 joule of energy is expended, digunakan. So the larger the value indicates that the larger amount of energy being used up. Alright, so you can see here by the expression, the average power can be calculated with the amount of work divided with the time. Okay, divided with the time. Now, in the case of instantaneous power, where time is very specific, whereby when we do delta time, okay, we find that 5 minus 5 exactly at 5 seconds, okay. So, approaching 0, so you find the expression turns to be differentiation towards dt, okay, dw work over dt. And when you open up the expression of what is, okay, delta work, you find that covalent to force times change in the displacement, so delta r dr. So when you divide with delta t, observe how the expression turns into V, right? So you find that this expression can be used provided now you have a constant value of force, right? Now we are going to see now how to do certain conversion. For instance, okay, though we can write watts as joule per second, is also correct to write down kilogram, meter per second, second. How do we even arrive and remember this expression, this unit, sorry? We can go with number one, the expression itself. Force is M times A and then V. So you have kilogram, A is meter per second, and then times V, you have meter per second. So this is V, and then this is A, and again this is mass. So hope this help you to understand how you arrive with an alternative unit for watts. Alright, now right now we are going to do a conversion of what we call as horsepower. Alright, so it turns out that some countries, they use up another unit which is called as HP, horsepower. Now, how you can either do the memorization by understanding 1 horsepower is equivalent to 746 watts, or just go to your calculator. At the back of your calculator, look for conversion number 29. You can straight away do convert it by using your calculator. Now, on the other hand, this conversion is given in the equation sheet and list of constant, if not mistaken. Okay, not equation sheet but list of constant. Alright, let's now look at another famous unit, okay, which is actually in the form of energy. Kilowatt hour. Now, kilowatt hour is actually energy and not power. But we find that in our bill, electric bill, it shows in this version because it's much easier. Okay, so it shows how much energy. Okay, So how much is it? Look at the K. So K is a number presented by 10 to the power of 3 prefix. Okay. Watts is just watts. Okay. How about hour? This is hour. So 1 hour is equivalent to 3,600 seconds. So 3,600 seconds times 10 to the power of 3, you arrive with this one. So in short, 1 kilowatt hour is equivalent to this value. This value. So if you were asked to convert, then it makes sense that 5 kilowatt hour is equivalent to 5 times 3.6 to the power of 6 joule. So that's how you do the conversion to joule. Okay. Now similar as this example. Now in example 8.11, what we are going to do is we are going to calculate power. So since we are going to calculate power, what we need to identify in this question is number one, our force, number two, the V value itself, if given. Alright, so let's now look at what's given in this question. You have a system which is an elevator where mass is 1,600 itself, and carrying passenger where the total amount of passenger is 200. So overall, it's actually the total mass is 1,800. Now there is a constant of friction force which is 4,000 Newton. 4,000 Newton. Retards its motion. Retard represent halang or obstruct. Means friction lah. So question, how much power? So obviously we are looking at force time V for a motor. So since it's asking for a motor, means that this force belong to motor. And where it needs to leave the car and the passenger at a constant speed, which is V itself. So we do know the value of V. However, the force of the motor remain an unknown value. So that's the first step. We need to discover the value of force. Now here, we need to understand the given figure that we have three forces: tension, friction, and weight of everything. Okay, weight of everything. Okay, where you will find that this tension is the one supplied by the motor. So therefore, force by the motor is actually the tension. Now in the first case, since it moves at constant speed, the term constant speed represent that acceleration is 0. Now according to the Newton's first law, to be correct, we are going to substitute the concept that net force in the y direction is equivalent to 0. And what are their forces? This is number one, tension upward minus friction minus the whole weight that it had to bear. Semua berat yang dia perlu tanggung. Okay? And equivalent to 0. And therefore, arranging the value of T becoming weight of everything plus the friction. Maknanya, the tension kena support both here. So according to this expression. So therefore, a simple calculation whereby if you would like to calculate power times with the V, which is 3 meter, and the whole weight is 1,800, okay, and plus the friction 4,000, you find that required power is 6.49 to the power of 4 watts. So 6.49 times 10 to the power of 4 joule will be expended in within 1 second. Now for question B, we will find that the scenario there is an upward acceleration. So the question still asking you power, however it's asking for instantaneous power, specifically at an unknown value of V. So in the process of calculating, we are leaving V as an unknown. So it's just a symbol. Leave V as a symbol. So our task now, we have to find the tension. Now, in order to find the tension, modify the Newton's law just now. So earlier equivalent to 0, this time is equivalent to positive MA because object is upward and accelerating. So again, similar to the previous case, tension is upward, friction and weight are both downward, therefore negative. Arranging it, therefore you will find this is the given expression. So substitute the value of acceleration 1 here, okay, and leave V as the V. So notice that you are leaving V as an unknown or symbol. Okay, when you do have any specific V, then only you substitute. Okay, V is instantaneous speed. Alright, so this is instantaneous power then. So what happened next? Okay, if ini if ya, the question do state that V is 3 meter per second, then you can now calculate the instantaneous power at that specific V, 3 meter per second, as this much. Okay, as this much. And you can see that if object is accelerating here, then you find that overall power would be larger. Alright guys, that's all for our chapter 8. Thank you very much.